you. Yes, it was a pleasure to be in Utrecht with Cheongs, or Cheong family. So I'm going to be talking about subquadratic algorithms for computing the diameter and the sum of the pairwise distances in planar graphs. So the talk is going to be quite algorithmic. So the context, of course, whenever you have a graph, you would like to somehow summarize some information about the graph. Similarly, when you have a distribution of values, many times you're interested in the expectation or the variance of the distribution. So you could think the same is interesting for graphs. So whenever you have a graph, you could be interested in some summaries like the number of vertices, the number of edges, the average, the minimum, the maximum degree, the diameter. So that's the pair of vertices that are farthest apart, which one is that distance. The average distance between pairs of points, so that's equivalent to the sum of distances divided by the number of pairs of vertices. The girth, the connectivity, you can think 1,000 such parameters. So here, as the title tells, I'm interested in these two objects, the diameter and the average distance, or actually what we will look at is the sum of distances. So we want to compute the sum between all pairs of vertices, of the distance between all pairs of vertices. So why this problem? So this comes in the context of fine-grained complexity. So recently people started looking, okay, there are problems we can solve in polynomial time, but the best running times we have are cubic or are quadratic. So is there some good reason for this? In the same way as there are some problems for which we don't know how to solve them in polynomial time, and then what we usually try to do is to prove NP hardness. So here we would like to prove some other type of hardness. And the way how this goes is, well, if I could solve this problem faster than, let's say, cubic, then I would be able to solve that other problem faster than cubic, and nobody knows how to solve that other one. So the idea is, let's build the theory just relying on a few problems that nobody knows how to solve them faster, and then show, okay, if any of those other problems I can solve faster, then these difficult ones I can also solve faster. So of course you want to build this theory just on a few basic assumptions, and one of the standard things is what is called the exponential time hypothesis, or the strong exponential time hypothesis. So basically it's once you have polynomial time, let's make a zoom and let's make a finer classification there. So they call this fine-grained complexity. This drawing is from the Simons Institute. They had a semester on this topic. So the result that is interesting for us is the following. So Roditi and Wasilewska-Williams proved that computing the diameter of a graph with n vertices and a linear number of edges, so it's a very sparse graph. If we can do this in something that is strictly subquadratic, so in n to the 1.99, let's say, then we could solve satisfiability with m variables in this is exponential time, but the base of the here is strictly smaller than 2. So if you could solve this in n to the 1.99, then here you could write 1.9999 to the number of variables. And this contradicts the so-called strong exponential time hypothesis, which basically, I mean, it's not really like this, but if it tells that the number you write here in the limit should be 2. So in particular, if you are able to write any number strictly smaller than 2, then you're contradicting this hypothesis. Okay, so this is actually just in one direction. So this is the type of lower bound I was talking about. So this is a problem computing the diameter for such graphs that nobody knows how to solve in subquadratic time, in a strictly subquadratic. And here what you're telling is, well, if you would be able to solve this strictly subquadratic, then the strong exponential time hypothesis is not true. So you would be proving something bigger. Something that is interesting actually is that the diameter here, the difficult case is already to distinguish diameter 2 or diameter 3. I mean, so even that case is difficult already. I mean, difficult, we don't know how to do in subquadratic time. So it's for small diameters that is actually difficult already. The same result, because of what I said, is also holds for the sum of distances. So to know whether in a graph all distance, whether the diameter is more or equal than 2, you can just reduce it to compute the sum of distances. The neighbors will be at distance 1, the rest at distance 2. And that tells you how much the sum of distances should be, should the graph have diameter 2. So then once you have this sort of lower bound, the question becomes, okay, so for which graph classes you can prove subquadratic algorithms? Okay, so in a way we are telling for sparse graphs, proving subquadratic algorithm perhaps is aiming too high, or you would be proving something extremely surprising, well, not extremely surprising, but something big. So perhaps I should tell the strong exponential time hypothesis is something where there is no consensus whether it holds or not. If you ask most people, is P equals NP? Most people think that it's not. There are some people who think that they are equal. If you ask out the exponential time hypothesis, which tells that satisfiability needs exponential time, then there is several people think that is true, that you need exponential running time. Some people think that no, and the percentage of people that somehow believe this hypothesis is decreasing over these conjectures. In particular, the strong exponential time hypothesis is the most controversial one of this, of course. It's the strongest assumption, so it's the one that gets the less support if democracy were to decide this. Okay, so in some previous paper, for example, we considered the case of tree width. So actually we considered this with Christian Nauer, and then also the problem was reconsidered by Abode, Vasilevsky, and Williams. Actually, they considered this problem. The techniques that are used were already presented here. We were not really discussing the diameter. So this was done a few years ago. So actually the time for this fine-grained complexity had not arrived. So this research was done before people started looking into these problems. And the result that I want to give you an idea today is that for planar graphs, this can be done in subquadratic time. And subquadratic means slightly subquadratic. So we do this in n to the 11 over 6. So that's a little bit smaller than 2. We are going to be doing an expected time, meaning the algorithm is randomized. There is one part of the algorithm that is randomized. And this will hold also if you have positive edge weights. But actually this is also the first result that is subquadratic also if you have unit weights on the edges. Okay, for unweighted graphs. So a bit of motivation on this is restricting attention to planar graphs is very useful nowadays. So whenever you have some algorithm for graphs, it's very standard to consider the planar graph version. An optimization problem like traveling salesman, computing the girth, computing connectivity. All these kinds of problems have been considered for planar graphs. Before this research, the best previous result had n squared and then log n to the 4 divided by log n. So it was not strictly subquadratic. And actually there was a follow-up paper that is in arXiv already available where they improved this exponent from 11 over 6 to 10 over 6. As usual, the good points of good follow-up work is that they provide also a better understanding of the result I'm presenting. It's not just that they go over my work and improve here and there a little bit, but there is a substantial progress that I really think that contributes to our understanding. In particular, here, for example, they also get the running time deterministic, so it's not randomized anymore.
Was the previous one randomized? Or?
This was not randomized.
And the one by Christian and the others, how does the tree width enter?
So it's the degree of the logs. So it's somehow n to the, n times log of the tree width plus 1 of n. Thank you. So actually, I have to tell this research here with Christian Nauer, and the one I'm going to explain today, actually, there is a general pattern that I like a lot, which is we use techniques from computational geometry for these graph problems. So in particular here, what was going on is that we needed to make so-called range searching. So you have points in some Euclidean space, and you want to figure out how many points you have inside some box. And the dimension of the space comes from the tree width. So this is actually a good introduction to this slide, which is this research and that previous one is somewhere combining ideas from graph algorithms and from computational geometry. So I think that I was able to do this research because I had worked on planar graphs before and because I had worked on computational geometry before. Otherwise, I wouldn't know that things exist. So in particular for planar graphs, I'm using several techniques. So something that is called an R division. I will explain in a second what this means, and this is a consequence of planar separators. I need to pre-process planar graphs for computing the sum of the weights inside a certain cycle of the dual graph. I need to use also dense distance graphs, which were introduced for planar graphs. I'm using a lot of the machinery that has been developed for planar graphs, but actually we will not need much of this. And then I'm using abstract Voronoi diagrams, which is a concept introduced in computational geometry. So I will come to this part. And to build these abstract Voronoi diagrams, we are using randomized incremental constructions. So that means I want to build a Voronoi diagram by adding the sites that define it in random order. So we will come to some of these ideas. So what is an R division? So this is a way to subdivide a planar graph. So let's say we have a planar graph, and then we have a parameter R, and then what I want is to break the graph into pieces. I want that each piece has theta R vertices, so linear in R, and then the number of pieces that I need at least is this much, n divided by R. The planar graph has n vertices, so you need at least this many pieces, and actually those are the number that you have. And then the property that you have is the so-called each piece has a few boundary vertices. So what is a boundary vertex? So this is actually a topological drawing. So you can assume that the planar graph is embedded in the plane, and then whenever you take a piece, you have the vertices that participate in more than one piece. Okay, so here in principle, I'm having this vertex that belongs to this piece and to the piece below. Having this vertex that belongs to three pieces. And I call these people boundary vertices. So this somehow models the interaction between what's going on within the piece and what is going on outside the piece. Everything has to go through these boundary things. And the idea is that each piece has like R vertices, but the boundary has a square root of R vertices. So the boundary is much smaller than the interior. Okay?
So you're partitioning the faces, or
you're partitioning the graph. So there are several versions, so I'm tempted to tell you can partition whatever you want, because there are so many versions. But in this case, I'm partitioning the vertices. Actually, I'm not partitioning because some vertices belong to several pieces. So a piece is a subset of vertices and the subgraph induced by those vertices. For example, that would be fine. Or a subgraph that contains those vertices.
So you're partitioning the faces, correct?
Sorry?
You're partitioning the faces.
Yes, that would be also fine.
But I think you can do it more generally, right?
So,
But each face of the planar graph will be in one piece.
if you wish, yes. You could also cut along faces if you wish. So actually it does depend. Okay, so if the graph is triangulated, you don't need to cut along faces. If the graph is going to be with large faces, you need to cut along faces.
Through faces.
Through faces. Yeah, so for the diameter, that doesn't really matter, because you could just, for example, triangulate where all the new edges have arbitrarily long length. If you, well, for the sum of the pairwise distances also.
So what do you mean by boundary vertices?
So the ones that belong to more than one piece. That's the definition of boundary vertex. So in particular, basically what you want is that any path that starts inside and goes outside has to go through a boundary vertex. That's a condition that you need.
But the pieces are topologically nice.
Yes, they can be topologically nice.
Every
They
edge
should
lies
be.
in a piece. There are no edges connecting vertices in different pieces.
So it could be means you could fix an embedding and then define the regions by closed Jordan curves. I mean the regions, the pieces. So that is possible. But the concept, the definition does not require topology. So the idea how you use, I mean, so this is a standard tool. The way how you do it is you use separators recursively. So you use a square root of n separator to break into two pieces, and then each one of those, if it has more than r vertices, you keep recursively splitting. When you do this, you might have the problem that some piece has too many boundary vertices. So then you need a weighted version of the planar separator, where the boundary vertices get weight 1 and the non-boundary get weight 0. And then you halve those. And then you count how many pieces you got when you repeat this thing, and it comes the correct number. And that's not obvious. Perhaps since you're asking, I should be warning you, a piece doesn't need to be something that looks like simply connected in the plane. So this drawing is misleading. So you could be cutting through a cycle, then you get a graph, and then you could be cutting through a cycle inside. And then you will get a piece that looks like an annulus. And then in that annulus you might have still to cut through another cycle inside. But actually, for example, you can also guarantee that each piece will have a bounded number of cuts. So the boundary is contained in a constant number of cycles. So there is a whole technology for this. It's a quite common tool. Okay, so this thing can be computed actually in linear time. For that you don't need to do it recursively, you have to do it bottom up. But actually in n log n is what you get if you apply this recursively. And for us this is not really important. Okay, so once you have the pieces, so this is one of these pieces. Actually the main result that I provided, and that's also what they improve in the follow-up papers, is a data structure for the following problem. So this is a planar graph, which in the application I'm going to make of the lemma, this will be a piece. And this has some fixed edge weights. So here I'm not going to change anything. This is part of the input data. So I want to pre-process this thing. And then at query time, I'm going to get the edges, the length of these edges. So at query time, I'm going to be telling, okay, so this edge has length 1, this one has length 3, this one has length 6, this one length 2, and so on. And I want to compute the vertex that is here inside that is farthest from this one. And I want to do that fast. Okay? Or I want to compute the sum of the distances from this vertex to everybody inside. Okay, so I want a data structure to answer these questions. So basically a query, I'm given the weights of the edges incident to this vertex, I'm given these weights. And then I want to compute, well, the sum of the distances or the farthest point from this one. Okay. So why is this important? So basically I'm going to take one piece, for example this one, and I'm going to pre-process it. And then whenever I take a vertex outside, let's say a vertex here, I want to compute the farthest point within this piece from this vertex. and somehow, this is the same scenarios we have there. So I can pre-compute the distances from this vertex to everybody in the boundary, and then I have that type of query that I'm studying. For the diameter, I want to compute the sum of the distances from this vertex to everybody in the piece. And for that, at query time, I will have the distances from this vertex to everybody in the boundary. How do I get the distance to everybody in the boundary? The other way around. For every boundary point, I compute a shortest path tree in the graph. Okay, so I will have all these distances I need actually pre-computed. So basically, this is the problem that we have to solve.
So it may be possible that one of these shortest paths from a boundary vertex to that vertex outside could go through the other boundary vertices, or could go
Yes. So that can happen. So in principle, the shortest path from here to somebody inside could go several times in and out. But I can just use the last time I touch the boundary. So basically, the last time I touch the boundary, I can just assume, when I'm applying this lemma, I can just assume that I have a shortest path outside that goes to that vertex directly. That will give me the same distance. Okay, so this is the data I have, and this is the query. This is the same as before. So we explained how to do this in pre-processing time, b cubed times r squared, where r is the number of vertices in the graph and b is the number of boundary vertices. So this is a running time that is very high. Actually, I don't really care what running time I have here as far as it's polynomial. What is important is the query time. I want to do it in time that is roughly proportional to the number of boundary vertices. So what I'm telling here is I want to spend time proportional to how many edges I have here, which is the same as how many boundary vertices I have here, not to how many vertices I have inside. The reason is the number of vertices I have here is the square of the number of boundary vertices I have. So it's important that I spend time linear in the boundary and not linear in everything. Okay? So that's what I'm trying to tell here. A pre-processing that would be polynomial, but much more than this would also be fine. Would also give you some subquadratic running time eventually. So the reason why this works, so if I go back, here, when I look at this piece, for every vertex that is outside, I'm going to spend time that is, for every vertex, I'm going to spend time proportional to the size of the boundary, instead of proportional to the size of the interior. And in that way, I'm gaining something. So if I have r vertices here, I'm treating r vertices by using a square root of r time. So that's the gaining. And for that, I can use a lot of pre-processing.
Excuse me, what is your model of computation? Is it
So,
bit cost or unit cost?
sorry, unit cost or?
Bit cost.
Bit cost. So it doesn't really matter. So that, because the running times, I'm writing them always as polylog. So I could use one or the other. Just by putting extra logs. I'm assuming that I can make additions in constant time. If they wouldn't be constant time, then it depends on the word size. But I'm assuming that I can make additions in constant time.
And sorry for following up. That still applies to the relation to the exponential time hypothesis, which may be also subject to the big model. Does that question make sense?
Okay, so in the original problem that they prove that you shouldn't be able to get subquadratic, that holds even when all the weights are 1. So as far as you have bounded weights, it doesn't really matter, as far as I know.
Thank you.
Sure. Okay, so the tool we're going to use are Voronoi diagrams. So this figure might be known to computational geometers. So if you're in the Euclidean plane and then you have some points that are usually called sites, then you can divide the plane into regions depending on which one is the closest site. So the usual motivation is that these are hospitals and you want to divide the population by which one is the closest hospital. Okay? So for example, points that are in this region, they have this hospital as closest. Okay, so it's a partition of a metric space actually, depending on which one is the closest site. So these are called Voronoi diagrams. And in computational geometry, this has been generalized to, well, I'm tempted to tell all sorts of settings. So you just need a metric space to define this kind of objects. Something that will be important for us is people also study the additive-weighted case. So whenever you measure the distance to a site, this site has an extra weight that you have to add up. So you can think like the hospital is at a 5th floor or 20th floor or 16th floor, so you have to pay also time to go up. That's an additive weight. And then at some point people realize, well, to define abstract Voronoi diagrams, you don't really need a metric, you just need bisectors. So whenever you look at two sites, you should be able to tell which points are closer to one site than to the other. And once you have these bisectors with certain properties for consistency, that's everything that you need to define Voronoi diagrams. So basically, the points that are closer to this site are those that are intersection of certain bisectors. So it's, a bisector that contains this edge, a bisector that contains this edge, and a bisector that contains that edge, this part. So bisectors is everything that you need. So I'm going to be using this for planar graphs. So the points that planar graphs, you can define Voronoi diagrams there. You can define them for arbitrary graphs, but in planar graphs, you will also have, the dual graph will be useful. Okay, so let's take this graph. Every edge has unit weights, and then I have 4 sides. So one is here, 2 is here, side 3 is here, and 4 is here, and they have certain weights, additive weights. So this has weight 0, weight 1, and 2.9 to get something generic. And then you can partition, depending, each vertex goes to one cell in the generic case, depending on which site is the closest one, additively. So for example, this guy here is a distance 1, 2, plus 0, 2. Here is distance at 1, 2, plus 1, 3. So this vertex has to go to this region. And you can prove certain things, like for example, these Voronoi diagrams, they should form a connected graph. Because basically you're taking a portion of the shortest path tree. So this is how a Voronoi diagram would look here. And the key point is that you can use the dual graph to represent this. So basically, because a cell, a Voronoi cell, it's connected, it has to be bounded by a cycle in the dual. And this is basically what these curves in the dual are representing. So here I'm assuming that whenever you have a planar graph, the first thing you do is you embed it in the plane, and then you work with that embedding, because otherwise you cannot talk about the dual graph. You also have the concept of bisectors. So this thing here is actually the bisector between this site and this site. So a bisector, somehow you define it through the Voronoi diagram of two sides. Whenever you look at two sides only, you have the vertices that are closer to one side, the vertices that are closer to the other. And then you have the edges where the transition happens. And those edges in the dual graph, they are a cycle. This part here is the bisector between these two sides with the weights, and this part here is the bisector between these two sides. So bisectors are curves that are defined by the dual graph, are parts of or are cycles, and edges of the Voronoi diagram are described by 4 sides. So this is an edge of the Voronoi diagram. I should define properly what an edge means here, but I will appeal to intuition. So this is defined, okay, so this is a portion of a larger bisector between this side and this side, and I have to tell where they finish, this bisector. So of the whole bisector, I'm just taking a portion. So the one that I get this thing, which I'm changing to another cell, and the one where I'm getting this thing, which I'm changing to another cell. So you could talk about Voronoi edges, and you could talk also about Voronoi vertices. Okay. And all the theory that was developed for so-called abstract Voronoi diagrams can just be applied here. For those that know abstract Voronoi diagrams, perhaps I should tell something. I'm assuming that the sides are in the outer face of the planar graph. That is important to apply the technique of abstract Voronoi diagrams, because abstract Voronoi diagrams, they assume that bisectors have to go to infinity. So I need that a bisector always goes through the outer face. Okay? So that's a technical issue, that I need that all the sides are in the outer face.
Do you need any relationship between the weights of the edges and the embedding?
No.
That's so the axioms of abstract Voronoi diagrams hold no matter what?
Yes.
Amazing.
So you just need that, well, it depends which paper you look. You need that a cell is non-empty. So in principle, this weight could be 1,000,000, and then the cell of this side could be empty. So that's something you have to take care of. But abstract Voronoi diagrams, you just need the concept of bisector. You don't need any metric. So in particular, it's a little bit overkilling to use that theory here. I mean, you could just work out all the lemmas again. But, okay. So Klein, Melhorn, and Meiser, they provided a randomized incremental construction of abstract Voronoi diagrams. In particular, I can use it in this setting. So what they argue is we can compute, well, so the consequence of this is that in our setting we can compute the additively weighted Voronoi diagram of a plane graph. As I was telling before, I need that all sides are cofacial, otherwise some of the axioms that they need here, they do not hold. And what is extremely nice about this paper is that they explain the number of elementary operations is, okay, the number of sides times log the number of sides. Elementary operations, but then you have to tell what is an elementary operation. And an elementary operation, what they show is that it's enough to have the Voronoi diagram of 4 sides computed. So basically, if you go back, for example, to the original thing, so you could argue what sort of operations do I need. So here, an edge is always defined by 4 Voronoi sides. So this edge is defined by this side, this one, and this one. So you could think like one of these elementary pieces I have in the Voronoi diagram is defined by 4 sides. And that's what they prove that it holds in the abstract Voronoi setting also. So what you need is to be able to compute the abstract Voronoi diagram of 4 sides. So in particular, they needed this because they don't want to make any assumption of the bisectors. And so the bisectors could be something for some weird metrics that is defined numerically. And then you need to tell, okay, what do I have to compute for this? So actually, in this concrete case, we could argue that the Voronoi diagram of 3 sides is actually enough. That's the elementary operation that you need. That's something that happens in this particular thing. And the output that you get is a combinatorial description of the Voronoi diagram in the dual graph. So what does this mean? The output is going to be, I have here a Voronoi vertex, which is defined by these 3 sides. Incident to this, I have a Voronoi edge that is defined by these 4 sides. And at the other end, I have a Voronoi vertex that is defined by these 3 sides. And so basically, the description of the Voronoi diagram is a planar graph given by this black thing, where every portion that has degree 2 vertices is given compactly. is given like this is part of a bisector. So it's a combinatorial description of Voronoi diagram where each piece actually comes from one of the Voronoi diagrams of 4 sides.
I'm sorry.
Yes?
I don't understand the second to last point there. So when you say that this is an elementary operation, the picture on your previous slide,
Yes?
constructing that is considered an elementary operation.
Yes. So if you would have 1,000 sides, to build the Voronoi diagram of that, you will need to build order of 1,000 log 1,000 of these kind of things for 4 sides only. It's a very non-trivial elementary operation. And actually what we do is we pre-compute all these things. So that's going to be a high number of pre-computations. But once you have pre-computed this thing, then you can compute the Voronoi diagrams in time proportional to the sides, log S. Okay, so how do you use this? So what's the point of this? So let's say you have a planar graph and you have this distinguished vertex, and I'm going to explain how these Voronoi diagrams can be used to build the data structure I need. So for every 4 vertices I have on the boundary, I'm going to compute all possible Voronoi diagrams for those 4 vertices. Okay? And actually I have to take into account all possible weights I could put here also. So basically for every 4 vertices on the boundary and every possible weights I could put there, I have to pre-compute the Voronoi diagram that I get. Now, you have this many options because basically what you're interested in is whether a vertex in the interior is going to belong to one cell or to another. So actually this changes discretely. In the Voronoi diagrams, it's just a discrete family of them. Even though a priori the weights can be an infinite thing, basically you're only interested in the difference between the pairs of weights of 2 sides. So you get these many Voronoi diagrams and you just pre-compute all of them. Now, when I get a query, so let's say I have here some weights in this edge, weight 4, 6, 4, and okay, some other weights. What I have to do is, well, I can remove, so I can remove these edges and I just put weight 6 here, additive weight 6 here, additive weight 4 here, and I compute the Voronoi diagram for this region. And now what I have is every vertex in this region, the shortest path to V0 is going to be using this vertex as a portal along the path. Every vertex in this region is going to be using this vertex as a portal. So this tells me if I want to compute, for example, the diameter, the farthest point from V0, what I have to do is I have to collect the point here that is farthest from this, the point here that is farthest from this, the point here that is farthest from this. For these ones, I have to add a 4. For these ones, I have to add, whatever weight I had here, and so on. So basically, the Voronoi diagram gives me a way to classify the vertices depending on which vertex on the boundary they are going to be used for, on the shortest path. Okay? And now the point is that I can compute these things in time proportional to the number of boundary vertices, log the number of boundary vertices. And that's where the gain comes. I still have something to do, which I didn't explain you how to do, which is when you get one of these regions, how do you collect the data? So how do you collect the vertex that is farthest from this one? Or how do you collect the sum of the distances from these vertices to this one? So you need to compute that, and that's an extra paper. So it's not trivial, it's not really difficult, it requires some thinking. So for the sum, it's actually easier. So there are tools that you can pre-process a planar graph such that whenever you take a cycle in the dual, you can count how many vertices you have inside. Using that here is also not trivial because this is actually not just an edge of the dual graph. This is a path, this is a portion of a bisector in the dual graph. So you have to add up this quickly over the path. So you need all sort of extra tricks. This is a very high overview only. So I was just telling, there are a lot of things that I just put under the rug. This is just a high-level overview. As I mentioned before, I like a lot from this research that I'm combining ideas from graph algorithms, in particular this R division, which is a standard for planar graphs, and tools from computational geometry, in particular Voronoi diagrams. So Voronoi diagrams is something very standard in computational geometry, but actually when I looked where it has been used for graphs, I only found a handful of papers. So it seems that it's a topic that has been used, but not very much yet. Here in particular, because we're in the plane, there are extra tools you can use, in particular the duality. So this extends to directed graphs also with positive weights. Also, if you have negative weights, can be done as far as you don't have negative cycles. When I gave this talk the first time, I said that this extends to surfaces of order 1 genus. Then when I was writing the paper, I realized that I would have to write another 10 pages. So at that point, I was not convinced anymore whether this is true or not. But actually, the tools that they provide in the follow-up work definitely will extend to surfaces of constant genus. There have been 2 follow-up works of this. One of them I mentioned already. So they are computing the Voronoi diagrams faster. That's what they do. They need less pre-processing. And there has been another follow-up work in Fox this year about exact distance oracle for planar graphs. So the question is, if you have a planar graph and you want to answer distance queries between 2 vertices in logarithmic time, how much space do you need to store the graph? And they could prove for first time that subquadratic space is possible. It's unclear to me whether sum of distances and the diameter can be done for H minor free graphs. So usually the way how I think that there is progress in research is first you prove things for planar graphs, then you prove them for graphs on surfaces, and then you prove it for H minor free. For graphs on surfaces, you still have duality, so you can still encode these Voronoi diagrams using the dual graph. For H minor, I have no idea whether there is anything similar, but to me it doesn't seem so. There are several problems for planar graphs for which we have, I would say, unsatisfactory answers. So in particular, this problem I worked time ago of computing n distances in a planar graph with n vertices. So you are given a planar graph with n vertices, you are given n pair of vertices, and you want to compute the distances between those prescribed pairs. So we know how to do this in n to the 4/3. It's not clear whether you can reduce this exponent. And something that I find, I would say, annoying is that in general for planar graphs, I'm not aware of any superlinear lower bound. So as far as I know, for planar graphs, we have no real lower bound that would tell you for this problem you need at least, I don't know, n to the 4/3 or n to the 3/2. There is a lower bound for dynamic problems. So if the graph gets updated, then some people recently managed to prove some lower bounds. But in general, for static problems where the graph is fixed, I'm not aware of any lower bound. And that's about it. Thank you.